Okay, so as a quick overview, what we're going to be looking at today, yes, I get it. We're going to be looking at supervised learning, unsupervised learning, and reinforcement learning. This is kind of basically talking about what those three things are. We're going to more in depth go into supervised learning. Most of the stuff we're going to be talking about through this workshop series are going to fall under supervised learning. And you're probably going to see that show up the most out of the bunch of things that we're going to go over today. And we're also going to talk through a case study today. Last time we kind of did a lot of more abstract things, talks from a very high level, but today we're going to actually see an implementation of some of the algorithms that we've talked about in sort of practice. And, and one of the things I want to address from last time, if any of y'all were at the session from last time, you might remember me talk about some gibberish with polynomial orders of magnitude making things better or worse fits, and that probably made no sense because it was just gibberish and I didn't give enough context for it. But I want to talk about it more closely today. So actually, let me open up the notebook from last time so you can kind of get a reference to that. So I remember last time when we were talking, we showed this model, and I had pointed out that oh, this model has a lot of parameters, and that gives it sort of imagine it to be higher orders of magnitude of polynomials, and it can fit data better. So what that actually sort of means is, let's say I have a bunch of data that I want to fit a function to. Like we talked about last time, we're sort of trying to find a best fit function with this machine learning method. And let's say we have this bunch of data, right? And imagine those are dots and things that we're trying to fit and not scribbles. So they're totally discrete. And let me try to do this a bit better. Nope, get out of there. So let's say it looks like this, right? And let's say we were trying to use our linear regression model again. And that was sort of just y equals mx plus b, right? That was our method of prediction. And basically, if we were to do our linear regression task method on this set of data, and we just tried our best to fit as many points as possible on some line y equals mx plus b, we would see what would happen is we would just perhaps draw this through, right? And what's happening here is we're missing this set of points. We're missing this set of points, and we're missing sort of the other points up there and below there. Basically, this linear method doesn't have enough granularity to kind of go through all the data points we want. But let's say we do something quadratic, right? Like y equals mx squared plus b. And let me use a different color, actually. So this is more hierarchical. Let's say we do y equals mx squared plus b. And with that higher order of magnitude, maybe we can draw a curve that looks like this now. And we've managed to fit more points and follow the behavior of this function more closely. And what if we now go to maybe cubic orders of magnitude? We do blah x cubed. And you see now we can go like this maybe, right? And we capture even more data points. We up that even more to something quartic, for instance, and we can draw this curve. And you see that we've sort of managed to fit more data onto our function by increasing the orders of magnitude. And you can sort of really see why increasing orders of magnitude can help you fit more complex tasks where the data isn't going to cleanly fall into a sort of linear frame of reference. Does this sort of thing make a bit more sense? Cool. So yeah, that's sort of the kind of clarification what was going on last time. Now let's look back at where we were here. So yeah, last time we sort of talked about very high level stuff. Let me hide this as well, so you don't stare at this in the corner. But so high level stuff, kind of what machine learning sort of is, and oh, and it's not going away on there, of course. So what machine learning kind of is, what it can do, how it sort of goes about doing that process, and kind of try to demystify a little bit, talk about some of the biases that are present in it. And today we're going to take an even finer look at it. We're going to talk about the three major categories of machine learning: supervised learning, unsupervised learning, and reinforcement learning. And have any of you heard of any of those terms before? Okay, so supervised learning basically is what we did last time, right? It involves some labeled data. We're saying, hey, given some data that maps onto some output, like we know that this one ought to map onto this one. We have labeled it beforehand. So for instance, some examples are like we have a data set of flower measurements and their corresponding species. So the data we have is pre-labeled. We know that this flower measurement corresponds to this flower species. Somebody had to beforehand go through it all and take a look at it. They had to manually label it. Same thing goes for something like MNIST, which is the 32 by 32 images of handwritten digits. Somebody drew up a bunch of handwritten digits that we want to use a machine learning algorithm to classify as a number. Well, when we were training our model, the data we trained it on was a set of data that was labeled. So somebody had to say that this digit, like this 3, for instance, was a 3. And so we know the correct answers in our training data. And basically, we're trying to discover a function that'll take our sort of inputs to our labeled outputs. Now, in the case of unsupervised learning, this data is unlabeled. So we basically just have a bunch of junk, and we have to figure out what to do with the junk. We don't know like necessarily how something maps onto something else, but we can do certain things such as segment the junk into 2 different cross sections and seeing if they actually fall into those categories. Like for instance, an example of this is online shopping purchasing recommendations. So you do this by this technique called clustering, which kind of falls under unsupervised learning. And as the name suggests, so what clustering basically does is it groups together items that are purchased together, and then it just kind of aggregates that to see if there's some sort of relationship. We don't necessarily say that, we don't tell the algorithm that, oh, people who purchase X are more likely to purchase Y, and then feed that data in. We just have some data where somebody purchasing X purchases Y as well, and we simply opt to group that together when we perform our actual classification. So I think a good example of that is like, let's go back to this little drawing. So let's say we had some data again, like this. We had maybe like 2 sets of data, and we were trying to figure out like, hey, if somebody purchases X, then maybe they want to purchase Y. And we don't want to have to do the supervised learning method of trying to label all our data. We can basically say that, oh, people tend to purchase these 4 things together. So if somebody purchases this, then they're going to want to purchase this. And I'm going to just recommend that to them regardless. And then based off their behavior, we'll see how well our clustering, this clustering algorithm actually worked. Like, despite the fact that we don't know explicitly if they're going to purchase that second item, we're just going to like use that, whether them purchasing it as our metric to validate if our clustering was good or bad. And so in this case, we don't explicitly label the data. The third sort of thing is this thing called reinforcement learning. And this is kind of entirely different from the first 2. You can kind of think of this as almost like an interactive thing where you have some agent, which is sort of the terminology, and our agent is kind of the thing we're trying to train to perform a task. And the agent is interacting with some environment. And what the agent is basically trying to do is to maximize the reward they're getting. So for instance, let's say we're trying to train our machine learning algorithm to pick apples. The first time, the machine learning algorithm doesn't really know how to pick apples. So it goes up and just smashes a hole in an apple. Our environment isn't really happy with that. So we don't reward the algorithm very much. So it's not happy with that. The next time, maybe it grabs the apple and kind of crushes it so that it's not really edible. But at least this time, it didn't just completely smash the thing. It has obtained the fruit. So we'll reward it a little bit more. And then maybe next time, it doesn't fully crush the apple, but it picks apples that are kind of rotting. We give it a little bit more reward. We tell it, no, that's still not the right behavior. And we basically cyclically perform this optimization until the robot now is able to go pick a ripe apple and not destroy and deliver it to us. And so you can think of it as like almost like a little carrot and stick thing. And basically this agent is seeking to maximize its reward that we can kind of give to it. Yeah, you'll commonly see reinforcement learning more so in like kind of games where the agent is maybe playing something like chess, or you might have seen like GTA 5, like AI plays GTA 5 or AI plays some video game. Those are typically done with reinforcement learnings because there is some very objective like task, like way you can reward this agent, and it can like freely interact with the things around it and see how the reward kind of propagates back. Any questions on those three kind of categorizations? So we'll mainly be going into supervised learning today. And the two things we're going to be talking about are regression and classification. And go away, terminal. Supervised learning is sort of like a pretty big domain. If you're working in a project, you'll probably be using some form of supervised learning. So last week we went over regression, which is sort of a very low dimensional kind of y equals mx plus b, given some set of things that map onto some set of outputs. How do we fit a function that's sort of kind of linear and abides by the mx plus b equation? And regression doesn't necessarily have to be linear. It's sort of defined just as the method of predicting some quantity given some input. Now, classification is different from that because it's about more of like assigning a class or a label. So it's some sort of categorization method. Instead of having like, you can think of it maybe as something that's more continuous, like regression, where we were trying to see maybe how a certain kind of input, such as like housing community or housing location, maps onto housing price, where you have this multidimensional input that's mapping onto this continuum of a bunch of outputs. Classification is more of just a categorization method. So for instance, like we see here where we have like something that is either hot or cold. There's only two categories. How do we predict those two things? And like we sort of talked about earlier, supervised learning requires labeled data. So we have to tell our model that given data X, we're going to get some output Y, and those are sort of the correct inputs to outputs. And so I guess in this sense, something that's interesting to kind of discuss real quick is this idea of sentient AI. So if we pull up this news article, we'll see I think this was pretty recent. So this is kind of an article about Google engineer talking about the fact that they believe that their company's artificially intelligent chatbot is sentient. And one of the pieces of evidence that this article presents is, let me see if I can find it. Basically, the robot says that it is sentient. Let's control F. I think it's the first quote. Nope, it's the first quote. Yeah, I want everyone to understand that I am in fact a person. Okay, yeah. So the robot says, I am in fact a person. Now, all right. Let's think about this real quick. Let's look at this from face value from this article, how this article is presenting it. Perhaps there is some background data at Google that informs this person more, but let's just look at it from this article. How do you think this robot arrived at the statement, I am in fact a person, if it were trained on some sort of like human speech? Yeah, go for it. Yeah,
As a result, if it says like I'm a person, it's acting like a person.
Yeah, exactly. So like in this case, it's just we're training this robot to try and make some connection between an input and some output, where the input in this case maybe would be some other text from somebody else trying to talk to it. And we've basically trained it so that it acts human. So we give it more reward. We say our algorithm is performing better when the robot acts human. So in fact, when it gives a statement, I am in fact a person, it's just trying to maximize the reward, minimize the error. So if we were to take this at face value, these sort of statements in the grand scheme of things are pretty meaningless, right? Because it's very dependent on how the robot or how the AI was trained to map inputs to outputs. Now, perhaps one day we could be able to find some crazy training data set that like establishes new connections and new consciousnesses and whatever, blah, blah, blah. And I mean, maybe that would be similar to how our brain generates new thoughts and neurons and all that. I probably said some more wrong biology stuff there, but that's okay. But simple statements like these, if we just consider it from what we've talked about for these workshops so far, they really don't mean all that much and shouldn't really be taken as any like evidence, I guess. So next time you go to like Thanksgiving and your granddad tells you that AI is going to come and subsume us all, just tell them that it's a function generator and this is all just BS, and he'll probably won't listen to you as usual, but that's all right. All right, so let's start actually looking at the things we're supposed to look at today. So we'll go to linear regression first. We talked about this pretty briefly last week. Basically, fx equals mx plus b. How do we model some input data to some output fx? So we'll just install some modules first, and we're going to generate some roughly linear data. And now, as a little segue, we're going to have an activity. I know, crazy stuff, right? So basically, this function here is generating some set of data points that basically abides by linear regression. And I want you all just to work with the folks around you, maybe pair up or something, try and figure out by just messing around with this function what the various features are, like what the parameters are. And of course, you could hover over it and use the built-in whatever to figure it out, and that works as well. But try to play around with it and see what tuning each of these parameters does. And yeah, we'll discuss this in maybe a minute. But yeah, talk to your neighbor. And yeah, William in the back there, who's unfortunately impeded mobility-wise a little, will try and help you out if you're stuck. But yeah, let's give this a shot. A little minute of discussion. What is this what are the parameters in here doing? Yeah, I'll take. So this one that's not good. Oh, were you able to run? I mean, where do you? Okay, so if I get more than percent sound. Oh. Oh, okay. I'll go. Once you get those back, I'll go. Okay. And tell them you don't have to on your. Okay. Like yeah. Oh, and that's a minute. Oh, I forgot about that thing. All right, so. What's up?
I ran over them and then they came out.
Okay, error right now. Cover the error.
And like actually I can't open computer open in a normal way, so then I can only go through adding on the prompt for some reason.
Maybe try going on Google and then uploading the repository into Google there. Okay, it looks like a lot of people are having problems with running the notebook in their own environment. So I'll show you all how to do it through Google Colabs, and that might fix all of the problems there. So let's try to do that real quick. Yeah, so if you go to this site, collab.research.google.com, right at the top left there. And go to upload. And then browse. And just go to that folder with all of the workshops in it and you click Yeah, you'll probably have to select all files. Let me see if you can upload all of these. Oh, you can't upload all of these. Oh, that's not good. Let's see.
So the thing is, when you try to run this, wow, you change it, it's gonna be all red, that's crazy. But the issue is, so you have to run this first install the properly. So. Oh, right, it's not gonna work. Okay, well, mine. And then another one. And then you get a model on that. Right? Then I did that. So it is a command that we have to.
Yeah. Let's go to Google Colab and try basically making a new notebook and then dragging all the files into this sort of like side file bar. And hopefully that works.
So do you just drag it?
Yeah, just onto this section right here.
Oh, so the file section is one.
Yeah.
And then so like the entire workshop two folder or just.
Just the entire workshop 2 folder. Yeah, the workshop 2 folder will be better. Just this one.
So do we have, we can use notebook and for that, and then I need to table of content?
No, so this files tab right here. It might take a little while because there's a good amount of data in there. But we will make do for the time being. Okay. Let's try. How many folks who are having issues are using VS Code? Okay. I'm thinking maybe we want to do a VS Code live share, but I think also it's going to be a mess. All right, you know what? For the time being, we're just going to look at what happens on this screen and look at these as a group because yeah, this thing is also pretty long and we don't want to keep people here forever. So let's just kind of regroup. And if your thing isn't working, just kind of look here for now, and I'll run through each of these activities as well. And maybe we'll just run through them as a group. Okay, so this datasets.make regression basically builds some roughly linear data. Now let's look at end features. Let's just make that 2 and see what happens. You see this kind of has widened a bit. Let's make it like 10. And it's even more wide. And back to 1. Now it looks more roughly linear. So what this number of features sort of thing is doing, does anybody have any thoughts? But are we still seeing the, let me make my thing light mode as well so you can actually see the graph axes. All right, be ready to be blinded. There we go. Yeah, okay. So let's look at the axes. If I make this 4, the sort of, it's more spread out, and you can see the axes actually are not exactly sort of the same as when we had n equals 1. They're like the numbers here were smaller, right? So it's not necessarily zooming in or out. Any other thoughts? What if we put it to 0? Okay, it crashes. Well, nothing insightful there. But yeah, so when it's just 1, it looks decently linear. And it looks, when it's 2, it's still linear, but a little less. Let's do 50. It's kind of a mess now. Yeah, so what's happening here with this n features actually is something we'll talk about a bit more later, but n features basically pertains to how many sort of like regressions are together in this one graph. So if each regression is like an M1, if one regression is M1x1, a second regression would be M2x2. And as you add more features, your sort of equation is basically becoming, for instance, an n features equals 2, it would be y equals M1x1 plus M2x2. So there's more like regressions being packed into the graph. The number of features is increasing. What do we think this noise is doing? This just from the word. As we increase that, what's going on? So this one is just making your data like more noisy. So if I increase it, there's going to be a lot more outliers that don't necessarily fall into the regression. Bias, that bias kind of connotates to the B term in our mx plus b. And the main thing I sort of want to talk about is this random state. So let's look at this graph real quick. If this is like just generating a random regression, do you guys notice anything as I run this repeatedly? Does it actually change slightly though? So it is not changing at all. So so is this thing lying to us? Like, isn't it supposed to be random?
Is that like a seed?
Yeah, exactly. It's a seed. So it's this thing called a seed. Let's change this 43 to a 47. Oh, and it's different now. And yeah, so what if we do 47 again? Oh, this is this thing again. Yeah, it's the random one decided to generate. If we do 52, no, it's different again. But what this random state thing is basically, it's setting a thing called a seed. And this is going to pop up a lot in your later sort of machine learning stuff. A seed basically is a way for us to deterministically generate random things. So if we want to explore some feature, like some random feature, and we want to investigate how our different algorithms act on it, we want to, oh, go ahead. Oh, we want to ensure that the random sample, we can investigate basically the same random sample over and over again. So every time we like try to do something, it doesn't like get messed into a different thing. And then suddenly like what we're looking at is different. So this random state is basically saying, oh, we are actually generating a random linear regression, but the random one we generate is always going to be the same one. Yeah, go for it.
Sorry, can you explain features again?
Oh yeah, so I'll write this out actually. We're going to talk about this later, but honestly, might as well talk about now. This looks like a better kind of place. So number of features, we saw from the graph that as we did more, invalid syntax, blah, blah, blah. Okay. So right now it looks like this. It's sort of somewhat narrowish. 2, it's kind of getting more wide. 3, it's getting bigger and bigger. So what's basically going on here is we have some linear regression y equals mx plus b. Now, for n equals nf, which I'm going to call number of features, equals 1, this is going to be like this, basically. It's just y equals m1 x1 plus b. There's only a single feature, a feature being this x value, this mx. And if I do nf equals 2, we're going to actually have y equals m1 x1 plus m2x2 plus b1 plus b2. So there's actually 2 regressions in here now instead of just 1. And so each feature is basically the x, the additional x that we have. And as nf goes up, we get more and more linear regressions. And you can see why this is making our plot kind of almost seem more like noisy. Because if we have a plot here, we had this one regression, now we have this regression, now we have this one, and this one, and this one, and this one, and it kind of widens. And we would expect it to sort of almost like converge this really thick, like voluminous, dense thing. So if I just do number of features equals like 50, maybe it'll crash my computer, maybe it'll actually show the point. Yeah, it just kind of looks like gibberish. Like there's so many regressions that it just kind of becomes like almost a brick.
So for each, like, each n is a different constant?
Not really. So actually, it's a different, like an additional variable is being introduced. So there's more x1s and x2s and x3s and x4s. So there's basically more regressions being put in together. Let me draw this picture again. I think this picture is most helpful. So when n just equals 1, we have this one regression, right? And you can see the points were kind of dotted around here, right? Now we go to n equals 2. Now there's going to be m2x2 plus b2 in there now, right? So there's going to be another linear regression in there. Maybe we have this one now, right? And this one's going to have this set of points. And you can see all of a sudden, if we just erase these two lines, that we have a wider kind of set of data points, right? Because there's data points that are fitted onto two regressions now. And as we add in more regressions, let's do maybe another regression, like maybe this line that we're going to characterize with these data points. You see that when we erase this line, the regression is now wider again. Yeah, go for it.
How does the computer generate like which new regressions to add? It's like a pattern.
It's sort of random. Like it's random, I guess, yeah. But it's gonna do it according to our seed. But yeah, like I mean, it's not gonna be like I sort of drew 3 lines that were all like in this, like all in the like sort of around y equals x, but it's gonna draw like ones that are like this and then like this, you know, and you can sort of gradually see why this is gonna kind of widen over time. Yeah, what's up?
Those are all preset based on the seed, right? So the seed would have like presumably a ton of lines drawn already, and then you changing the number of the noise would just enable and just those lines.
Which is like
Or sorry.
Sorry. Okay, we're gonna let's go one question at a time. So the seed actually isn't like the seed doesn't. We don't have a bunch of pre-computed things that we classify under seeds. We actually just randomize something and then we assign a seed to it, and it's sort of like it's like stored in like this. It's stored under the seed. So then when we access the seed again, we know it's going to do the same random thing, but the seeds aren't pre-computed.
Okay. So like there already exists like a bunch of lines, and then the more features you enable, the more lines that sort of show up.
Yeah, exactly.
Okay.
Yeah. And sorry, was that a second question?
And I was just like, thinking the way I process it is like the first you get you choose the number of features there are, and then after that the noise function comes in, and that's when like I think becomes more wide after that.
Yeah, exactly. So like if we add in even more noise, the high amount of features, you're basically going to have even more of a brick, right? Because each feature is now going to have a chunk of noise surrounding it to widen even further. So yeah, it's true. Bias is basically a B term. Oh, it's like the y equals mx plus b, the b. Yeah. So oh, I mean, we say bias equals 20 here, right? We could put like 30, 40, 50, 20,000.
You did 0
without putting randomly, so like it's harder than it comes out for like a
Mhm. Yeah, no, you're still going to get the same thing. Like, but this time you don't have it stored under a seed. So when you rerun the code, you're never going to get, or not never, but it's highly unlikely that you'll ever get the same state that you had last time because you aren't storing the state.
like be sure that we're like getting the same random state and the number doesn't matter.
Yeah, the number doesn't matter, but you just have to access the same number every time. Yeah. Yeah, it's up.
That's biased.
Yeah, because Mark, it's going to be reused later, I bet. Yeah, but it doesn't matter. Yeah. What's up?
So the average device is only the average Y value of
So the bias being 20 is like all the regressions that we're going to plot, their B values, so their y-intercept is all going to be 20. So we basically know that all the regressions we plot are going to go through like 0, 20, like this point, for instance. Yeah. And that's what the bias term is defining. Yeah, what's up?
So you can specify how.
Yeah. How does each feature determine what seed?
A certain seed.
Yeah. Uh-huh.
When you specify this.
Uh-huh.
What is that?
Oh yeah, the random state. Yeah, yeah. Gotcha. Yeah. So a way you can sort of wrap your head around that is there's nothing. Let's just think of the fact that there's nothing pre-computed. There's no random state yet before we make the regression. Now we make all the regressions, and there's just some random regressions. So we now have this set of regressions that are defined by some equations. After we have those, we slap a seed on them. And then when we revisit the seed, we can basically just reconstruct our recipe. The seed wasn't there before we had finished generating all the lines. But then at the end, we tell it that we want to just recreate this process. And the seed like gives us the method of recreation. Like the seed tells us this, we're just going to slap this back on there. Like, okay, let me try to make this a bit more clear.
So does a 52 seed does the same thing with seed 52? Do they get a different one or the same one?
No, the seed is local to you.
Oh, okay.
Yeah, it's not, sorry, it's not a universal thing that like everybody abides by. Yeah, like if you guys see, if only this notebook worked, it would be really easy to demonstrate because I would just have you all do the same seed as me and your graphs would all be different from me. Yeah, but if you guys did that same seed again, you would get the same thing. Yeah, they wouldn't look alike. So you can all confidently do seed equals 47 and like be sure that nobody is gonna like have the same thing as you and like hack you or something. What's up? Okay. So the seed is this random state variable. That's what I did. Did you know? Do you know what the random state is? We were talking about it earlier. Okay, so basically it's a way of labeling like this trial. Like if let's say we were trying to flip a coin, right? And we flipped the coin 4 times, and the 4 times the things we got were head, tails, tails, head. Now flipping a coin is a non-deterministic process, right? When we redo that, we're not going to get the same thing. But by setting the seed, by setting those set of trials under a certain seed, we know that if we call that process again and we tell the process that the seed is the same, it's going to basically deterministically recreate that trial. So it's a way of letting us keep track of random data that like so we can test it consistently. Okay, so that was really good investigation, but let's get a move on. So yeah, this is sort of what we were talking about. So linear regression, basically same thing, except in machine learning, we're going to call that m value W a weight. And that's going to sort of, as we talk more, it's going to look more intuitive and understand why it's happening, because basically the features, like the various x1s and x2s, when you have some data with multiple features, for instance, if we're trying to predict housing price by the amount of swimming pools the house had, the community it was in, what the weather was like, those are 3 distinct features, and they may not have the same weight in the determination of the housing price. So basically what that weight value does is it scales the importance of the feature X in sort of different levels, and it determines how heavily a certain feature is going to be weighted. And that's why we call the M a W a weight. Does that make sense? And so we define a linear model here. This is supposed to be an exercise, but we're a little short on time, so I'm just going to write this up. Return M times or W times X plus B. Basically, just return the linear regression output. And so let's try and classify our data, our N features. Let me make sure this isn't messed up. Oh yeah, this is messed up. Okay, so 1, regular linear regression data right here. And we're going to make some linear model, and we're basically going to try and use our linear model to classify this data. Now, just eyeballing it, right, we don't really know what our W, our weight term, or our slope is going to be, and we don't really know what the bias is. So let's just make some random guess. Let's just guess that our data is fitted by some regression 2x plus 10. And let's see what happens, how well it does. So yeah, we feed it a 5 and we'll get a number. And let's make predictions on that data set. We get this bunch of data. And then let's make predictions compared to our actual data. And basically, so let me just explain this column. There probably should be a picture here to make it more clear, but we have Y pred and we have Y. So X, given some input X, we're sending data to Y. And these are the actual outputs. With our random linear model that we just guessed above, Y equals 2x plus 10, these are the Y predictions that we're getting for the input X data. And they're pretty wrong. They're pretty terrible because we just guessed some random numbers and they suck. And so that's the sort of illustration of like the sort of what's going to happen when you're kind of iterating over a machine learning model and training it and giving it sort of the first pass when you give it a random guess. It's going to look pretty ugly. And you can see here, it's like visual inspection. these two things are not close at all. This is called Y prediction, but it's not really prediction. It's pretty trash. Yeah, question.
I ran the code, like my model only returns -1.
Yeah, because there was supposed to be an exercise up here. That was like where you were supposed to just write up the regression yourself. But yeah, if your notebook is actually runnable, just copy what I typed there, and it should run smoothly. Yeah, it's up.
I'm having issues where like the X from a previous cell doesn't translate to the same X in like the cell below. It doesn't recognize the X as the same thing.
Ooh,
Like, well, if you
interesting.
define something in a previous cell,
Yeah,
and you don't define it in the next cell, it doesn't carry over.
it should carry over.
Yeah, it says like, oh, name X is not defined. So like, the function of the cell items. And then kind of like, oh.
All right, well, I'm just gonna sweep that under the rug and make you look at this instead. But yeah, so our random guess is pretty terrible, basically. And so, okay, we saw it was bad. And well, if we think of what we talked about last time, what we talked about earlier, right? We know that the model has performed pretty terrible, and we need some way to tell it that it's doing bad, and we need some way to quantify exactly why it's bad. So the way we're gonna do that is we're gonna do it through basically methods of computing this thing called error, which is basically how do we quantify, error is how we quantify how far off our predictions are from our actual values. And so sort of the really just like no-brainer way to do it is, why don't we just subtract the prediction from the actual, take the absolute value and just call it a day, take that as our term. That is one way of calculating error. That's called absolute error. Basically, if we just looked up here, okay, this is 26, this is 10. Our error is just going to be 26 minus 10, 16. This is 20, this is 10. Yeah, error is basically a way of quantifying how sucky our model is. Like, and we want to minimize error so that our model is accurately fitting the data.
I have a question in general. Is there like a lot of linear algebra in machine learning?
Yeah, so machine learning is fundamentally built on linear algebra. Machine learning is just linear algebra. The good thing is though, is that machine learning is so ubiquitous that you don't have to know anything, right? You can like,
It'll do it for you.
yeah, it'll do it for you, right? Libraries like TensorFlow and PyTorch, which are sort of pretty big libraries, they just have all the linear algebra wrapped into all their methods. So you can not know what's actually going on and be able to do it, although that's not recommended, I guess. But you can get by, it's fine. It's okay. But yeah, so that's just the absolute error, right? And we can compute that. And you see like 16, 10, 14, just a subtraction. And we take the absolute value so the negative terms don't like clash with things. And then we just average it. Oh, mean. Okay, the mean error was 16.39, which is pretty terrible for a linear regression. But we don't actually use that. We use this thing called mean squared error. Okay, now this is a big equation, so with a summation and all that, and we don't really want to, you can omit your eyes or whatever. Basically what's happening is we're subtracting and then just squaring it. So we're taking y pred minus y actual, basically what we're doing in the absolute error case, and then we're just squaring that. Exactly, and then to calculate the mean, we just add all of them up and then average them out. So does MS mean squared error or MSE, does that make sense? Not too complicated. And so discussion question, why don't we just stick with absolute error? Why do we have to do all this like stupid junk? Why do we have to square it instead of just like taking the absolute value and just calling it a day? Any thoughts on that? Yeah, go for it.
If we set the absolute error, then like all the values and negative values are going to come out and that's
Well, because we're taking the absolute value afterwards, so they all sort of go to positive. But yeah, I would see if you're just not even doing absolute error, if you just did regular error, that'd definitely be a big problem. Yeah, go for it.
It's not like when you're like calculating error and you have like a data point from here, like you calculate the radical, which is the square, and then the distance from the line on both sides. So the square gets both positive and y in the error. Like that.
That is true. Like when you calculate like the distance between two things, I guess.
The distance is only in one direction, and because it's error, you have to count for both directions.
Not really, because in this case, we're just looking at like one-dimensional outputs.
Oh.
But okay, so those are all that was good point though. But so the actual reason why we don't just stick with absolute error, there's a good amount of advantages with mean squared error. So one important aspect actually is the derivative. The absolute error is just going to be some x. Like for instance, if we took the absolute error, we don't have anything squared. We just have the variable. And when you take the derivative of that, it's just a constant. So it's meaningless. But with the absolute error, we have some variable squared, right? So when we take the derivative of that, we still have some relationship that like has some sort of trend. And why is that helpful? Well, we want, but basically machine learning is an error optimization process, right? We want to ensure the lowest possible error. So if we have some differentiable function that we quantify our error with, we can utilize that for optimization's sake to kind of like skate around and find the lowest point in the optimization. Yeah. I mean, but like, hey, if you can do ddx like x squared, I think you're in good shape. Can you wait? Okay, not to put you on the spot. Oh, okay, we're not going to go there. And there are some other advantages, like when you take statistical variances and stuff, when you have squares, it's helpful, but that's not super relevant here. The derivative thing is kind of your like a big part. Okay, so let's do some mean squared error. And there's an activity here that tells you to implement the mean squared error. We're not going to do that. I'm just going to copy it from my answers because I honestly don't even remember how to do that in pandas off the top of my head. So we're going to find it in my answers doc. And ooh, there you are. We're going to just paste this line in here. And if you're following along, you'll just want to type this thing in. And so that's the implementation of mean squared error in pandas. And if we do that, you can see, okay, we have a bunch of zeros. Oh yeah, because I set it to 0. Good job, me. If we do that, we will see our loss pop up as a mean squared error. Basically, what we had, remember we had a 16 here last time. Well, it's now 16 squared. We had around 10 here, it's now 10 squared. That's sort of the only thing that's changed in this instance. We can take the average of that again. Oh, 456, that's our loss. And yeah, it still sucks. It's not really, we just squared the previous loss, so yeah. Now, what we're gonna do now is, what if we tweak the variables and do some different things? Well, let's designate a new x, m or w of 10 and a new b of 15. Try again. Oh, well, look at that. The loss is lower. It's 185 now. And now hypothetically, if we just kept iterating through a bunch of loss values, not a bunch of loss values, a bunch of w and b values, we would eventually iterate to some local minima of error that we are satisfied with. And that would basically describe our linear regression. And that's basically how a machine learning model learns. I'm going to sort of try and demonstrate that real quick with some drawing. So let's say we were trying to perform linear regression on some set of points here. Let me use this one. Blah, blah, blah. And let's say we start initializing our model. And the first thing we do is we say, okay, we're just going to make some random guess and we're going to say, bam, it's that. And then we're like, oh, that sucked. Let's try something else. And we go, that. Oh, it got even worse. Maybe instead of going that direction, we go this direction. We say, oh, it's a little better now. And then we say, oh, let's continue trying that. So we go here. Oh, it's even better. And we go here. Oh, it's really good now. And then we say, oh, maybe we keep pushing it to try and do better. We go here. Uh-oh, it's not so good anymore. And basically, after each cycle, how we quantify how good it is through that mean squared error method. And if we look at it in terms of how the loss is changing, I want you to imagine that we have almost like a parabola, and what we're trying to arrive, and let's see, I'm going to label some axes. And this is sort of the loss or the error. And our initial random guess has a high error here. Well, we want to just basically try and come into this divot, this minima, right? And with each subsequent trial, if our loss continues to decrease, maybe we keep following along in that direction until eventually we oscillate out of the curve and you say, oh no, we're getting worse. Let's go in the opposite direction. and we keep going and going and going until we arrive at this final sort of optimal point. Does this process sort of make any sense?
It's like if you weren't doing calculus, like you're just like instead of use randomly guessing, you use.
So it's not really randomly guessing. So this is sort of a very simplified expression, but yeah, like method of explaining it. But yeah, it's almost like that. It's just trying different things until it arrives at some local minima for loss. Yeah, it's up.
So does that mean if you use mean square of error, you can just like, is there a way to get your machine learning program to just find where the derivative is 0 and then that would automatically minimum error?
No, so it's not really like as simple as a derivative. So this loss thing isn't actually like purely a derivative. It's kind of like what I've drawn here. It's just like an illustration of how a loss changes over time until we get to like a minima. But so there actually there isn't really a way to just say like this is the minimum of loss, because when we iterate each time, we are actually constructing the loss curve, right? We don't know what the loss looks like when we try different things. We have to actually try them and see how the loss changes. So we can't really just say, oh, this is the local, this is, we have some predefined loss curve, which is fine where it's 0. But yeah, that is the last sort of little parabolic like minima that I just drew there is pretty kind of important to the whole machine learning thing. So if you aren't clear on that, like please ask questions and we'll try to sort through it a bit more. Okay. So yeah, we can basically, like right now we're sort of manually doing the learning process. We can tweak our model parameters until we get to some minimum. And machine learning models actually have their own methods of doing it. But let's just try something in like a sort of prepackaged way. So let's just make some more data, or sort of have our old data. These are our inputs that we were looking at. These are our y actuals. So there's this thing called sklearn, which has a lot of pre-built machine learning algorithms kind of packed in there. This is sort of an answer to the, do you need to know linear algebra to do this? You don't, because they've already built in this stuff for us with linear algebra. So we can call scikit-learn and we can tell it, hey, I don't want to try random parameters. You do it. Fit my data for me. We run the linear regression method in scikit-learn, and it's not giving me what I want to see. All right, so I want you all to use your imagination. Imagine that scikit-learn just fit like a really pretty line on that like bunch of data points we had earlier. Oh my God, it's so beautiful, right? Yeah. Thank you. Yeah, I know. It was all scikit-learn. Okay, cool. So we just basically told scikit-learn to call this fit method, which fits our data and gives us sort of the optimal loss and the best linear regression. As you can see, it looks really good. So yeah, we can look at what weights and biases the linear regression model settled on. So in the end, it decided that y equals 17.167x plus 20.0038 was the best linear regression to fit that bunch of data up there. Now we can check them against what the actual values are. Oh, and yeah, it's pretty close. And so basically, scikit-learn using the fit function has learnt the parameters that define the linear regression. And it didn't get like exactly on there because remember we set that noise equals 10 parameter. It's not a perfect regression. So there's some noisiness surrounding it. Oh, that's a good question. Is it usually better? Not necessarily. Yeah, not necessarily, because like on here it looks a little bit better. But it might be able to actually, because the thing is when it tries everything, it's going to realize where I guess in this sense, we're kind of getting in the weeds here, but when it's trying things, perhaps a pattern we'll see is that the bias, it can basically set, since the y-intercept, it's always going to go through there, and maybe it'll try to generalize that y-intercept, which is why it's getting pretty close on the bias. Yeah, so. Oh yeah, because that's the thing, because the random, your random seed is different from mine. Or like even if the number is same, the number is local to me and local to you, so you have different numbers. Oh, there we got a little demonstration of that. All right, what's up?
Because like when you generate features, all the lines cross through 0-20, but they all have randomly different slopes. So maybe it's easier to find the starting point as opposed to level slopes completely different.
So for this one, this was only one dimensional. So there was only one feature. Sorry.
Oh.
But I mean, yeah, if there are multiple features like that, I think that would also be the case because your features would always have one point that is
Yeah,
like
always have
0,
one.
20. So yeah, so there's some like almost like a bias towards finding the bias. Yeah, what's up?
Coefficient, the actual coefficient, where do we get the actual coefficient from?
Oh, you remember above, like way above, let me scroll up actually instead of just pointing up. We defined a linear regression up here with just some coefficient and a predefined bias. And so the coefficient, like we just let sklearn like make the linear regression, but like we can re-access the coefficient because we stored it here. So yeah. Yeah, what's up?
Okay, so you're actually adding, okay, so for the y, I just want to clarify, so the equation that you wrote earlier, y equals m1 x1 plus x all the way up to like mi x, right?
Yeah.
That is correct, right? You just add them all up together, right? You don't plot them. Okay.
Exactly. Yeah. Yeah. They're sort of different x values feeding into them, but they're all like in one equation. They're all in like one chunky equation. And
Wait, so, okay, so you end up getting like some that you end up obviously wait, the x values are different. Okay.
yeah. So okay, let's talk about this a bit more. This is pretty important, so we can kind of spend more time in it. But so for let's say, let me see. Let's say we have some task. Let's go into our case study. Actually, let's just look at our case study. This stuff doesn't really matter all that much. I'll just explain that later, but let's look at this case study. Okay, maybe we won't scroll that far down. Never mind. Let's say we're trying to predict housing price and we have that set of variables, right? We want house price and we have street, we have zip code, and we have number of swimming pools, or let me make this something a bit more like archaic. Number of, we'll do something even more like number of toilets. Yeah, okay. And basically each of these things is a feature. So street is a feature, zip code is a feature, number of toilets is a feature, and they're each going to get a X value. And we're just going to still look at this from the linear regression frame, but so they each have an X value. And with that X value comes their own W value, their weight. And what this weight is doing is it's basically saying how much does this feature matter? So which of the three do we think matters the most out of street, zip code, and number of toilets for predicting? Okay, zip code. All right, guys. I know you all put a lot of value in toilets, but we'll just say zip code matters the most. So let's assign zip code a high weight. Let's give it 10. And what? Okay, I'm just gonna say it. Street matters more than toilets.
No.
All right, fine. Toilets matters more. We'll give toilets a 6, and we'll say street matters the least. We'll give it a 2. And let's say they all have some associated bias, and this honestly doesn't really matter that much. We'll just say they're like 2, 5, 17 or something. Now I give toilets the most, so I hope you all are happy. When we write our equation, y equals w1x1 plus w2x2 plus w3x3, what we end up seeing is this equals 2x1 plus 10x2 plus 6x3, and then plus our biases that I'm just going to call B. And we see that like we don't really need to write out the bias terms individually because they just sum up and it's cool. And typically in machine learning, your features, your x1, x2, and x3 are going to be about on the same scale. They're all like, maybe they're all going to be between 0 and 1. And so we see here, the feature with a higher weight, the one that's more important, is going to be overrepresented in our prediction y, right? And so zip code is going to matter the most in determining the housing price, and then toilets, and then streets. So that's basically how the different features with their weights contribute to finding the actual prediction.
So is the x1 like actually?
So the x1 is actually just how the street is mapped onto our math. The zip code is the actual input zip code that's transformed into some way that can be represented in our math. And same with the toilets. So these are the x1, x2, x3 are distinctive things that all feed into the prediction of y. Question?
So do you do this with the n features is equal to 3? Or
Yeah, so you would get this if you say n features equals 3, for instance, in that earlier linear regression generation. So there are 3 features in this case, yes.
then how would could they choose exactly those 3 features in that order? Is it because like it's gonna be a table and
Well, so the ordering, this doesn't matter, right? Because it's linear and we're summing. But like in your own, if you're actually performing a task, you would know that you have these 3 inputs. So you're gonna give it 3 feet, like you have 3 features basically, because that's all the data you have. Yeah, so
So you wouldn't be able to map this, would you be able to map this just like a 2-dimensional like X, Y? Because X's are different, like.
yeah, but they're all like X values, right? They all factor into in the same way. So
Okay, I understand. You wouldn't be able to, wait, how could you, the X's are not this.
yeah, let me demonstrate this pictorially. Okay. Yeah, so we have x2, which is our street. We have x1, which matters the next, or not x1, toilets. Toilets matter the next most, x3. And then we have x1, which is the street, which matters the least. So x2 matters the most, right? So let's just, we can just look at this as 3 separate regressions first. We'll just say this one, first and foremost, is what we said above, y equals 10x2 plus, and we said the bias was 5. And we'll just graph this on here, right? We'll just say 5 and then slope of 10 looks like this about, right? That's our first feature. And we're going to graph our second feature as well. This one is y equals blah, blah, 6x plus 17. And we're going to graph that on there as well. That's going to look sort of like this, maybe. And then we're going to graph our third one. Y equals 2x1 plus 2. And that's going to look roughly like that, right? Okay, that's not a good representation. That should look like that roughly, right? And we can first look at these as 3 distinctive linear regressions. And then when we actually look at how these 3 features feed into predicting our y, since they are this linear algebra term known as a linear combination, we can combine all 3 of them together into a single line, right? But based off how steep these slopes are, when we combine them, our combination line is going to be skewed towards the one that's steeper and bigger, right? So let's just, if we were to add every single data point together on each x value, right? If we added all the y's, maybe this would, like if we were to add them and average them out or something, or if we just purely added them, our output line probably would look something like this, right? And that's how we see that this output is more heavily weighted towards the street and the toilets and the zip code more, because the linear combination is closest to those 2. And even though those 3 x's are different values, they're all graphed on the same axis and then recombined into one line.
My question is how can they be graphed on the same axes and they're like, yeah, I guess you just do it. Okay.
Yeah.
Yeah. It doesn't actually get like the exact things, but it gets as close as possible. Because it goes by one function that maps to all the data sets, right?
Well, yeah, so like we have this axis and then we just drew like all these x's, like they're all on the x-axis, right? They're just different input values. So they all combine into one thing in the end. They're all consistent with one another. Even if the x's are different things, it's like we just plotted 3 different lines. They aren't the same line. Like we don't interpret them as the same line initially. But yeah, so blah, 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 blah. And then why is linear regression not a good idea? Well, linear regression only fits linear data. If we have quadratic data, we aren't going to fit it well with a linear thing. And you can sort of demonstrate this to yourself. We have this little quadratic function. You can generate sort of different orders of magnitude of, like if I wanted to make this, like right now it's squared. If I had a parabola, and I try to stick a linear thing through it, that sucks. As I increase it even more, No. Bad. Doesn't work. It's not very good. So linear regression only will fit linear models, linear data well, but it won't fit cubic or quadratic or anything like that well, because it's not really going to follow the behavior of the curve. Yeah, what's up?
Go back up a little bit. I have a question.
This
Okay.
one?
I'm more. Back to the graph. Okay. So let's say we have our final graph, right? Y equals, right?
Line.
Yeah, the purple line, right?
Mhm.
Okay, let's say we're trying to use that to predict, like, let's say, right, for example, what if, like, for example, we said the street matters with the least, right? But what if, like, basically my question is like, okay, let's say, for example, like, a street was like 10, like a lot, okay?
Yeah.
And, like, zip code was like 2 or something,
Mhm.
okay? And it closes off with 2.
Yeah.
Right? Would that not, like, be like a really high value, even though, like, zip code, like,
Yeah, so it's going to be a high value, right? But it's going to look the most like the line is going to look the most like the most highly weighted graph, right? So like here, let me expand this a bit. So let's say we had these three lines, right? And we had this line and then we had this line, right? And if we added all of them together, right, they would be bigger than all three of them, right? But the bigger one is going to end up looking like this, right? Or let me draw this in a different color.
right, if the zip code is like, if the zip code X is plotted on the same axis on the other two, as the other two X's, right? If you have, sorry, not the zip code, it's the street, right? Whatever, for example, right? If the
Mhm.
street value is like really, really high, this X is really high for that, right?
Yeah.
The value wouldn't actually be high, but like on the line, it would be.
Well, the street value itself isn't really like the value of the thing on the graph isn't really necessarily a raw measurement of the street value. It's just how much the street value is weighted when it comes to predicting our output. So when we give street value a lot of weight, then basically we're saying that our output, this combination of all three factors, it's going to take into account street the most, because you see this line, right? If this one is the street one that's really high, this line that we get by summing all three of them is going to be closest to street, right? So if we were to imagine it this way, right? If we removed these two lines and we only looked at street, they honestly would be a pretty decent predictor of all three of them factoring at the same time, because the other two aren't weighted that much. So they become sort of slightly more negligible as compared to street, right? And then when we do weight them, we might get closer, but it's not that far away from just looking at street, because street takes up so much weight, because it's like we've decided that it's very important. Yeah, so.
And the input you're putting in is not the street number, but it's a value representing how important that street number is.
Yeah, that's the weight you're designating. That's so the WX is actually the raw street value that's then weighted, and it can be up weighted.
It's like a bunch of X's, a bunch of sample X's.
Yeah, your data set is going to be a bunch of sample X's.
So the sample X's won't be the actual street number. It'll be something that quantifies how important.
No. So WX is going to be the thing that quantifies how important. Like the W itself is the quantifier of how important, but the street is just going to be like some raw value. Like let's say we had like, okay, this is getting a bit too into the weeds, but let's say we had like we were making a classifier that predicted if something was a hot dog or a chicken. What we're going to do is we don't really care if the model actually says it's a hot dog or a chicken. We just need to be able to differentiate between both. So when we make our labels, we're just going to say, if it's a hot dog, it's a 0. If it's a chicken, it's a 1. And so we've managed to transform our data into something that's machine interpretable and still maps onto our inputs, even though the inputs are hard to interpret, right? And that's what you're going to be doing to the street address. So like if you have like a street that's like Holt or something, right? Maybe I will take this and transform it into some matrix corresponding to your like letters. Like this will be like maybe I'll just call it 17, 8, 12, 2. And you can encode different streets like that, and that'll be your input data. But when you apply a later weight to it, like when you multiply it by W, then you upweight the value by more. But yeah, so blah, blah, blah. And so yeah, the way we can sort of think about it is we've already talked about all this, but like when you have all these different features, they're just making their own contributions to how we get to that output Y. This is sort of like the key image here that sort of sums it all up. Basically, by feeding these values and these features and combining them together and weighting them in different manners, we can determine how important they are and how much they contribute to the output y function.
Okay, and all the machine is doing is predicting the weight.
Yeah, it's just predicting the weights and the bias that we want to apply overall. That's all it is, right? It's just given some data, and we know we're performing linear regression, just come up with some W and some B that gets us closest to the outputs that are the actual outputs. And we're going to look at a case study here. I'm going to run through this kind of quick because we're a little low on time, but this is real estate data. And basically, it has all these parameters, ID, MS subclass, MS zoning, blah, 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 blah. And we want to use all this data to figure out, what are we trying to figure out again? Sale price. So how much is this house going to sell for if it has certain features? And we're going to try to use linear regression for this task, which, I mean, do we think that's a good idea? If we have all these features and we want to predict like sale price?
No, you try it.
It's probably a pretty crappy idea, right? Because this task is sort of complex, right? Sale price isn't just going to be a linear function of some features. There's going to be a lot of quantities, and it's probably going to look sort of non-linear. But you know what? We're going to try anyways because we are talking about linear regression. So,
No shame.
We get it done.
all right. So these are different sort of features we have. We have kind of ignore some of the more archaic ones, but we have stuff like the shape of the lot, the neighborhood it's in, the material, the roof. I mean, big stuff, you know. And then we can plot. These are our variables. So on Y, we have the sale price, basically how much like it actually sells for. This is supervised learning, remember? So our data that we're training on is labeled. So these are our labels, basically. Ooh, this one, yeah, this one's pretty expensive. Oh, yeah. We can just plot two of them together. This is sale price as a function of lot area. So what happens to sale price as your lot increases? They're all kind of clustered around one thing. So this actually isn't very informative. Ignore that. We'll talk about it next time. Plot some stuff. So this is the same thing. We can plot the overall quality of the house, which is our other output with the lot area. We see this one is a little more nicely clustered. Okay, let's just not do any work and have the library do the work for us. We call scikit-learn fit again. But this time we have to sort of pre-process our data a little bit. Don't worry about this too much. This is just some engineering going on so that, like, you know, I talked about we have to transform like hot dog into 0 and chicken into 1. This is sort of what's going on here. We're splitting up the data. We're performing some transformations on it. So it's machine readable, basically. Because our computer is stupid. It can only read like numbers like 0s and 1s. So we have to give it something that it can read. But yeah, so we make our linear regression model again. We fit it. All right. Thank you for being broken again. Change presentation. Does this do anything? That doesn't do anything. All right. Let's just imagine again that there's some housing scores, and this time it looks really bad. It looks terrible. Oh my God, this thing sucks. All right. And we can actually validate that with this R² score, which is just some stats thing that just tells us how well the linear regression fits the data. And it's 0.648.
Not bad.
It's not bad. It's not too bad, but like, yeah, no, that's a p-value thing. That's a different thing, I think. But yeah, no, that's actually that's a good point. That's a common test. Like, is it better than a human? Like, that's all the machine learning algorithm. Like, people sometimes validate by metrics where it's like, oh, it's 99% accurate. But honestly, a lot of times you just have to beat a human, and humans are pretty crappy at a lot of things. So like, your work sometimes isn't that hard. And okay, let's try to get through this last little bit. But earlier I skimmed over it, so you guys probably didn't see it because I was going too fast. But earlier we also took out some test data that we didn't train on. So the model hasn't seen this data before, right? We segmented the input data, so we had a little bit that it's never seen to validate on. And why do we do this? Why do we not just test it on data it's already seen? Well, that's kind of bad, right? Like if I were like trying to make a model that could make predictions on later inputs that like are from the real world or something, giving it data that's already seen before can be potentially dangerous and can be like not a good way of actually quantifying accuracy. Because if we just give it stuff it's seen before, maybe it has like some sort of memory pertaining to those specific items. So to actually get a sense of how good our model is, we have to test it on some testing data that it's never seen, that we've segmented our input data from out of and set it aside with. So let's see. Okay, it's not that bad, but it's not very good. Okay, so I mean, yeah, so these two honestly aren't horrible, but they're not great. So maybe I was a little harsh here. Let's imagine a linear regression that's like not really that great, but not too bad either. So yeah. So, okay, let's go and just try to predict it. Predict what stuff looks like. If we give it a house with a lot size of 10,000, we tell the model that the quality is around 5. And then we shove the info into the model we trained and we tell it to predict it. All right, it says the house will sell for 132,000. So yeah, I mean, we just made a machine learning algorithm, right? We trained it on some data, and now when we feed it some new stuff, it tells you what it's gonna sell for. It gave us an output variable. Now, this is probably like not good. It's not very accurate, as we saw with our assessment scores, but I mean, it's something. So
Something's better than nothing.
yeah. But yeah, so
Is it two? Did we create the thing for overall quality, or did another machine, did another model?
so the overall quality, if you look up, is like okay, I'm not going to scroll up again, but the overall quality was part of the data set. That was like an input.
Oh.
Yeah. So we're just conditioning it off of these two features, overall quality and lot size, for instance. So those are the different X's that are being fed in. So we tell it those and we say, hey, how good is it? But yeah, if you got this notebook to run, you can say, oh, I trained a machine learning model today. And if you didn't, which is probably the majority, you can also just say that and pretend that you did. So yeah, any questions? We're gonna conclude here today. Yeah, so we actually only got through half of this whole thing. There's another section on logistic regression that's this long, but we'll just put that until next week and then just make the series 1 week longer because there's way too much stuff to cover in one session. But yeah.
Thank you.
Yeah, you're welcome. All right. Yeah, but this is all just math. Like once this sort of early introductory kind of workshops end, there's probably going to be like a set of like special